Good afternoon, everyone. Distinguished guests, dear speakers, and all participants. Welcome to IZPHOTECH 2025, annual celebration of World of Photonics here at İzmir Institute of Technology. It's great pleasure to open this year's meeting, organized jointly IZTECH Department of Photonics, IZTECH Optics and Fotonik Society OPTICA Student Chapter, and IEEE Photonics Society Student Chapter. Over the next 2 days, we will host outstanding researchers from academia and industry, who will share their insights into the science and technology of light, from cutting-edge photonic material to real-world application shaping our future. Before we begin, I would like to invite our distinguished guests to stage for their opening remarks. Firstly, I would like to invite Professor Dr. Yann Amouroux, Head of İZTECH Department of Photonics, to deliver her welcome address.
So, hi everyone. My respectful and dear Vice Rector Cem Hocam, Professor Dr. Cem Çelebi, dear colleagues, dear guests, and our precious students. It's such a pleasure to welcome you once again to the İzmir Institute of Technology for our annual celebration of World Day of Photonics, IZPHOTECH 2025. When we first started this journey in 2022, our main goal was simple, adding the third tool. The first two were light point and late light meetings, conference series of us, which actually, according to the news that I gained a few hours ago, have reached more than 3,000 clicks. One of the seminars given during the late light conferences, and to raise awareness, share knowledge, and connect people around the science and technology of light. What began as a modest event has now become a vibrant international gathering with friends and colleagues joining from all around the world. And yet, some things never change. Every year, I still get the same excitement, the same butterflies, as when we first welcome our graduate students back in 2017 and our undergraduate students back in 2019. At that time, explaining what photonics wasn't exactly easy. Together with our students, we spent a lot of time answering questions like, is it about photons? Or did you say botonics? Well, the latter is not still is not still erased, but yeah, we are doing our best to increase the awareness of the importance of photonic science and technologies. Here we are in 2025 with photonists, light scientists, and engineers who not only understand what photonics is, but also pushing its boundaries. Seeing our graduates now working in academia, in industry, and in research institutions across the world reminds me that our biggest success is not just in the labs, but in the bright people who started their journey here, two of whom are among our speakers this year's event. This year, IZPHOTECH once again reached around 200 registrations, a clear sign of our growing and passionate community. Among these, approximately 50 participants come from our sister department, Gazi University Photonics program. For those who may not know, there are only 2 undergraduate photonic programs in Turkey, here at İZTECH and at Gazi University. And both continue to interact and attract talented young minds each year. Since 2019, the university entrance ranking thresholds have improved 40 to 67% for the Department of Photonics. Numbers, I think, reflect both academic excellence and the rising enthusiasm for photonics in our country. This year, IZPHOTECH brings together 15 scientific talks, 11 of them invited, covering the photonic materials, devices, and system. For the first time, we are also including student oral presentations alongside the poster sessions we began last year. I'm especially proud that we are hosting an outer workshop this year designed to help our young researchers navigate the world of scientific publishing, because good science deserves to be well told. Of course, none of this would have been possible, especially as a free of charge event, without the incredible dedication of our students and the generous support of our partners. My heartfelt thanks go to Optica, the IZTECH Foundation, Optics, Technotip, and the IEEE Photonics Society for standing by us every single year. And of course, to our students, our organizing heroes, I would say, who once again proven that light travels fastest when guided with passion. Our celebration of Day of Photonics is more than a conference. It's a bridge between science and education, between research and application, also known as between technology readiness levels of 4 and 6, which some of you might know as the mysterious valley of death. Luckily, photonists do not fear darkness. We just bring more light. So, dear colleagues, friends, and students, thank you for being here or connecting through your computers. I wish you an inspiring, enlightening, and enjoyable IZPHOTECH 2025. Let's appreciate the importance of photonics in our lives. Thank you.
Thank you very much, Professor Yann Amouroux. Next, I am honored to invite Mr. Yann Amouroux, the Optica Europe Director, to share a few words.
Thank you. Thank you. Good afternoon. My name is Yann Amouroux. I'm from Optica. It's a few words, but it's a very brief few words because I know we are running a little bit behind schedule. I just wanted to reflect on a little bit on the words that we just heard from Professor Farikli, because I think you had a lot of very nice quotes, and they really represent what this is all about. This is about a community-driven event. In this case, students that are supported by faculties, which is always a good mix, because this is where you're going to grow into the next generation of leaders, and the work you're doing, it's all part of that training. So these are really good opportunities to learn new things and to develop new skills, because it's not easy to organize a meeting. Is very, very difficult. I'm sure like some of you have found out, it's like, oh, I have to organize this. Oh, nobody told me about that. So well done. It's really good. So I think the main slide, and it's just that slide. It's just that you are part of a very, very, very big community. And photonics, it's it's kind of a mix on so many things, optics, photonics. The big number of 572,000 is where we at Optica, we kind of estimate that's roughly the size of the community, because those are people that either publish, attend a conference, take part in a seminar or a webinar. They're not necessarily members. It'd be great if we had a society of 600,000 members, would be absolutely fantastic, but that's unrealistic. Our society is about 24,000, 24,500, depending, which is quite good. The community is really what drives us as what we are, and we're not the only one. There are other societies. IEEE was mentioned. There are others like SPIE, and some of you are maybe a bit more into chemistry. Then you will have SES or physics. You have AIP, APS, IOP. There's hundreds of societies. All of us, what we're here for is to support the community. So the work, the research you put in, we want to make sure that we give you the right platform and it's published in the right place. Then your efforts are seen by the community that you want to target, the people that you want to touch, and supporting you as well to progress. Because when you publish good research, you will probably move on and you could go into industry or you could go into academia, but you need to demonstrate that you understand your subject. So this is where societies are quite important. As an organization, we organize many conferences. Actually, this week in Prague is the Laser Congress, which is a really good meeting. So you have got all that. That's all happening. There's loads of different meetings. You could be, if you really wanted to, you could be at the conference every week, and I'm sure many of you in this room would be agreeing with that. It's not possible, but it could be done very, very easily. The point in the middle of the screen there, you can see we have over 400 Optica chapters. So we have currently about 420 chapters globally. And this is a global society. You are part of a global network. And those are there is an opportunity for you to connect with people anywhere in the world. So this is the key point. What's happening this week, today and tomorrow, you're going to connect with your peers. There's many people online that would like to be in the room, but it's an opportunity as well to connect with others, to pick up an M, get in touch. You like this presentation, you like their poster, have a conversation, talk, communicate, network. That's really important. What you're going to do now, today, tomorrow, is going to help you in a few years' time or even a few months' time. Some of you are planning the next step, you're about to finish, and then you're thinking, oh, I want to do a master's. This is where you got to start looking and always look around, and the opportunities are there. There's a lot happening. The photonics and the optics community is a fantastic world to be in. You will be amazed by how many vacancies there are to fill. And I heard this morning some really exciting plan about developing industry kind of photonics here in Izmir, and those will be absolutely wonderful. So it's things will happen, and it's happening. So that's it, really. I think I don't want to take any more of your time because, as I said, there is limited amount of time, but there we are. So that's a little bit about Optica, and I look forward to meeting a lot of you over the next couple of days. Thank you very much.
Thank you, Mr. Amouroux, for your inspiring message and for Optica's continued support to student chapter around the world. Finally, we were planning to host our rector, Professor Dr. Yusuf Baran, for the official opening. Unfortunately, due to unexpected urgent commitment, he could not join us today. Instead, we are very pleased and honored to have Professor Dr. Cem Çelebi, Vice Rector of İZTECH, with us. I would now like to invite him to stage for opening speech.
Hello, everyone, dear guests, dear students, and dear members of two beautiful societies, IEEE and Optica. We are very happy to have you here at the IZPHOTECH event, and also we are very much excited to have this a few days beautiful event based on photonics and optics. As our student already mentioned, our rector, due to his last-minute change in his program, and now I'm together with you, I brought his love and greetings, and hopefully, which will continue as a very good, happy event with these beautiful words of our rectors. I'm actually one of you. I'm a member of your family. I'm a physicist, and I'm working on experimental optoelectronics based on two-dimensional materials. So therefore, it's very important event also for me. But because of time constraints, I don't want to elongate my speech, although I prepared about 45 pages to have a 2 hours talk here. And hopefully next year at the next IZPHOTECH event, I will be more than happy for being one of the invited speakers to give you a brief information about 2 hours on my research here at İzmir Institute of Technology. So please excuse me because of my next words, because as the vice rector responsible for the research of İzmir Institute of Technology, I should say a couple of words about the scientific outcome and scientific production of our institute. İzmir Institute of Technology is one of the research universities in our country, Turkey. We are always within the first 5 research universities among 21 research universities. So the number of publications per faculty at our institute, according to the number of scientific publications per faculty, we are also ranked as number 1 among all other state universities, and we are very happy to taking place at the first place of this scientific article per faculty. And besides, considering the grants per faculty for European Union projects, we are also at the first place in all the universities, not only the state universities. So therefore, especially the research and the studies based on optics, optoelectronics, and the photonics related subjects are one of the most important scientific outcomes of our institute. Therefore, I would like to express my special thanks to Professor Canan Varlıklı, who is the head of our photonics department, for her great encouragement and for her great work to contribute to this great success of our institute. And once again, I would like to thank you all for being with us today. And I would like to say, may light be with you. Thank you so much.
Professor Çelebi, please stay on the stage for a moment. We would now like to present a small gift of appreciation of Mr. Yann Amouroux for his kind support and contribution to our event.
So where is the guy with optical device on the hand? Okay, we go there. Wow. Thank you very much. We are very pleased to have you here for your support.
Wow.
Hocam, can you come in front of the logo so that I can talk about it? Yes, that's good. Yeah. Okay. Thank you very much. Once again, thank you both for being with us today. And to all our participants, welcome once more to IZPHOTECH 2025. Let's make these 2 days full of learning, inspiration, and collaboration. Enjoy the event. Now I would like to bir dakika. Hocam siz. Şimdi Koray hocamı sahneye davet ediyorum.
Burada kalacağım değil mi?
Evet hocam.
Çalışıyor hocam. Altta bir şeyler katmıyor mu?
Good afternoon. I'd like to thank you all for attending the IZPHOTECH conference. Before I start, I always take a selfie with the attendees. So if you can, maybe if I go onto the center and take a selfie and give your best pose. No, I need light. So. One, two, three. Okay. Actually, it's a great pleasure to be at IZTECH for this wonderful event, and also the day of International Day of Light. So it's a great pleasure. It's first time visiting IZTECH, and I've already met with students and faculty and enjoying my time so far. And it's a great honor to give the plenary talk. And I would like to thank you all for coming and who are here in person. And also, I guess we have an online community that are following this event. So hope you enjoy this 2-day event. So I'm actually from Turkey, and I spent my undergrad and grad education in Ankara, Bilkent University, and then since then I moved to US, worked at Caltech, I think IZTECH and Caltech. And then as a postdoc, and I've been at Northwestern as a faculty member since 2011, and actually became full professor as of this September. So it's a great honor, I guess, to come back to my country. And I've been kind of like in a tour. I've already gave a seminar in the other photonics department, Gazi University. So I think I feel lucky to have given talks in 2 of the photonics departments in Turkey and get to know the faculty and students. Today I'm going to talk about some of the research on the area of metasurfaces, and in particular applications related to imaging, sensing, and quantum. Before I start my talk, I would like to thank the students. Yesterday, I mean, they invited me. They all made all the arrangements and then picked me up from the airport, dropped me in my guest house, and then kindly offered me to take me to Urla, so we get to enjoy a nice night with students. Let's see if the laser pointer, yeah, Sümeyye, Efe, and Olgun, and also all the other students who worked hard. I know that the student is run by undergraduate students, which is, I think, a big feat. So if you can give a round of applause for all the students just for their hard work. Okay, so I'd like to just start with what I do, and I think I don't have too much time, but I work in the intersection of, I would say, photonics and material science and applied physics, and we cover a broad range of topics in the as of materials, platforms, but we have three kind of like important steps that when we do our research. So we use electromagnetic theory to design or understand how light interacts with matter, materials. That will be useful for like making new devices. Of course, as an experimentalist, you need to be able to make them, so fabricate these structures and devices. So we rely on nanofabrication tools as we work on nanophotonics. That requires advanced fabrication facilities. And then, of course, you need to be able to characterize them and see how light indeed propagates in different materials and devices. And we work with optical materials and a lot of different platforms, which some of you, which I will touch these today. And of course, as you all know, photonics plays an important role in many applications, from displays to quantum information science and many others. So my research group is working on different areas. So if I were to discuss this in like in a quadrant, here on the top left, these are novel electromagnetic design techniques that we utilize. I'll talk about inverse design briefly today. We also use machine learning aided photonic design. And we also are involved with collaborations that allow us to make materials and devices using novel fabrication techniques. So in addition to conventional nanofabrication technologies, we utilize DNA assembly in collaboration with chemistry department and a 3D nanoprinting by using 2-photon lithography. We work, of course, with material scientists and different range of materials, quantum materials and phase change materials. So here I list the publications that are on the past 10 years or so. And then we have metasurfaces and plasmonics as platforms that we use to understand, again, how light interacts with materials. So I guess I don't have to introduce you the importance of light and photons and then their application areas. So this is kind of, I picked the colorful photos that I can find on internet about the applications, ranging from lightning to displays to energy. Then we have the photonic integrated circuits, and more, recently emerging technologies like AR, VR, LiDAR, and Li-Fi. So photons play an important role in many application areas, and I think that's good for us as researchers who are passionate about, if you're passionate about, solving Earth's energy problem, that you can find a photonic solution, or you're interested in, let's say, biomedical. So there's, I think, always an application and motivation for photonics researchers. You just need to pick your problem and then, be motivated and dedicated to address that problem. So the problem, I want to say the problem, but the conventional optical components are often, limited in functionality and are bulky. So I picked three, I guess, optical devices that rely on either ray optics, geometrical optics, or ray optics. And prisms, lenses, and mirrors and gratings, they have the scale that is either comparable or larger than the wavelength of the photons. I don't know if this keeps coming. Is there a way to get rid of this? So as a researcher dealing with nanophotonics, I think I always put the slide to kind of give a perspective about where I'm interested in terms of the scale. So here you see three different scales, and if you compare A being the size or the minimum feature size of the devices is much larger than the wavelength, then you can use ray optics and geometrical optics. And then if it's comparable, like this like in this morpho butterfly wings that essentially scatter and reflect light because it has these electric contrast because of the biomaterials have different optical refractive indices yields to these bright blue color. And then in the nanoscale where the structure is much smaller than the wavelength, this is the area I spend most of my time in my research group and thinking about how we can utilize these nanoscale interactions to control how light propagates and engineer for either novel or enhanced functionalities in photonic materials and devices. So here is a famous Lygerkus cup. So this is essentially a glass with nanoparticles of gold and silver, which are, giving these different colors. So it's the same cup. It's just where the light sources makes the difference. So for example, on the right, there is a light source, bright light source inside the cup that essentially, absorbs the blue and red. Therefore, you only see the red light, blue and green. So if you think about, blue, green, red, once the blue and green gets absorbed, you only see the red light coming through. And here, the same particles also strongly scatter. So you see that if you have the light source outside the cup on the left-hand side, then the same particles also strongly scatter due to the plasmon resonances that I will briefly touch. So here you can see there is an optical effect happening at the nanoscale and due to strong light matter interactions. So the title of my talk is on matter surfaces, and this matter surfaces is loosely defined, but I will touch base on some of the applications. And you can think these matter surfaces as nanoscale antennas and elements that change the phase, the intensity, or the polarization of the electromagnetic wave. So for those who are familiar with the electric field expression, so let's say you have a sinusoidal electric field. So here you have the intensity along X and Y direction. There is, of course, a phase angle to it. And then, of course, the polarization depends on the ratios of these intensities as well as these phase angles. So think of these elements as a tuner, like a passive tuner, but then each element, once wave hits, for example here, change it differently so you can decorate a surface with these spatial arrangement of these little antennas and resonators. And that the promise of matter surface is that it's a surface, so you can significantly reduce the size, the thickness, and therefore make these flat components. You could have, of course, making it thinner allows you to make it lightweight and compact, allows easy integration with electronics. Hence, you can, with the reduced materials and processing, you can have a sustainable solution to whatever problem you're interested in. And of course, with the potential of being low cost, right now, of course, the fabrication costs a lot, but there are technologies that are trying to make this much cheaper. And there are many applications. So for those interested in matter surfaces, there is this nice review article published last year in ACS Photonics called Roadmap for Optical Matter Surfaces, and highlighting some of the important applications. Some of you also I'll talk today about. So for example, I have an edge detection section. I have an imaging section. I have something that resembles a quantum source, so we're getting there, but so I'll try to highlight within my own research group some of the work that we do. And I think that's pretty much the, getting to the end of the introduction part. I would like to just give you an important distinction between a metal and a dielectric as it relates to the discussion of how light interacts with materials. And I know that we have a lot of undergraduate students. I'll try to make it as accessible as I can, but forgive me if I fail to do so. So metals, if you think of metals as an optical material, You could probably only think of mirrors as they are bright and shiny when you excite, with a broadband light source. And therefore, it's boring as for any optical application. And however, it turns out that, like as I showed in this famous Liangcai cup, if you take a metal and shrink it to a nanoscale, the metals having a lot of electrons, free electrons due to their bonding structure, once excited with, let's say, an electromagnetic wave is nothing but an oscillating electric and magnetic fields. So suppose this small metal nanoparticle, of course, you have negative charges everywhere. You have an electric field that oscillates back and forth, right? So an oscillation, let's say this is our polarization direction. So once you have an electric field, then of course the negative charges will move in the opposite direction of the electric field, leaving behind a positively charged. So you basically distribute charges to the right and to the left. And of course these, but the oscillation, these charges oscillate back and forth. And at particular wavelengths, you get this, what we call plasmon resonances that allow you to have a strong electric field enhancement. If you have this plus charge, then there would be an electric field from the positive charges to the negative charge, building up this strong electric field. And what that strong electric field does is that it enables to interact photons with the material at the nanoscale. So this is an early plasmonic metasurfaces paper back in 2011. On the other hand, you can also use insulators or dielectrics to induce resonances. So typically in my research, we deal with resonances because if you want to do something with photons at the nanoscale, the size mismatch is huge, right? So nanoscale, let's say we're talking about 5 nanometers to 100 nanometers. And for photons, we're talking about visible being 400 to 700 nanometers. So there is a size mismatch. So you need to bring this huge waves to a small, tiny scale. So you need to have some strong interaction between the waves and the materials. So one way to do so with the electric materials is that you can use a high refractive index material that can, of course, the wavelength scales with the refractive index, lambda divided by n, right? So if you have a high refractive index with a small size, you can focus light and bring light down to smaller scales, and then hence we can induce what we call Mia resonances, and then that could be used to build up the electric metasurfaces. So with that, I guess a required introduction to introduce what metasurfaces are, what the material choices are, I would like to discuss 3 directions that relates to imaging, sensing, and quantum applications. And let me first start with the inverse design and direct laser writing. So this is our kind of like first generation metasurface work, which then led to other directions as we move on. So this is, when I talked about this, controlling the resonances and being that the size, for example, here what we have is a nanorod and a silver nanorod, and we are making simulations where we change the nanorod width and we can simulate what would be the reflected phase shift. So we have nanorod antenna, and the wave hits, and then if you know there would be a phase change upon reflection, and you can calculate through electromagnetic simulations how the phase will change. So blue being 0, and then this is 2 pi phase shift. And essentially you can map out what the required phase shift for a given nanorod width. And of course, you can write down the generalized Snell's law for reflection, which gives you the reflection angle as a function of the required phase distribution. So what we did is, and then what we're interested in was early on to have what we call a rainbow reflection. You send a broadband light to a surface, and then that the waves get diffracted or reflected at one particular direction, as opposed to two for a diffraction grating. If you were to have a diffraction grating, light comes in and then you would have right to the right and to the left. Here, you're getting what we call an anomalous reflection, again, by carefully controlling the size of these antennas. So this is kind of like the schematic that resembles a trapezoid shape, in which we essentially continuously change the width, right? So if you think this, you have a narrow size here and a wider range here, that allows us to have a gradient phase that is matching with the desired reflection phase. And of course, once we are done with this design, we fabricated this using electron beam lithography, and here you're looking at the scanning electron microscope images. And this is the meta surface in action in our lab. In free space, we have a broadband light source coming from this side, right? Hitting here, of course, there is coming with an angle, and you can see that the reflected light is kind of like is going in one direction, so you don't have any light reflection coming in that direction. And you can also see it here in action. We have a broadband light source coming here. We have our meta surface sitting, and then here you can see most of the light gets reflected to a particular direction. So with a 75% conversion efficiency. Now, this is actually a nice transition to the next topic, which this particular one was a plasmonic element, a metal. So the plasmon resonance are typically associated with metals like silver and gold. And the next topic is going to be about the electric. So here you need to work with the reflection mode. So because the metals are lossy, once you send light, the light gets absorbed and then you get a very low transmission. And here you have these parameters A, B, C. And early on for this modeling, we were using the conventional forward design. But if you were to make an optimization, since you have many parameters to optimize, that essentially becomes a computationally expensive method. So at the time, we were interested in, is there a way to use what is called an inverse design, being that you have an input and then you don't know what the material is, but you want a specific output. And what you need to do is essentially to solve for the Maxwell's wave equation within this region inversely. So you start with the output, and there is an optimization algorithm such that you need to find the distribution of permittivity, which is related to the optical refractive index inside this material, and the electric field as a function of the position in these structures. And we solved that. So again, I don't have too much time to discuss this in detail, but we developed this algorithm and solved for this particular problem. And here the problem, the first paper was what we call a beam splitter. So you have a black box, and the property that we were interested in. Let's say you have an unpolarized light. So you have a way polarized that is along the horizontal or parallel direction, and then one electric field along the normal direction. And you would like to split these two polarizations into two different directions. And hence, it requires a specific phase distribution within this so-called black box. And once we did do that, and this is essentially for the electric material, which is a polymer, has a refractive index about 1.45, and it gave us this weird shapes. So, and this is kind of like the structure, and we fabricated this using the 2-photon lithography. I think I have a better, yeah. So here, if you look at these kind of like the simulations to show how different polarizations. So you have a plane wave that has containing both parallel and perpendicular polarizations that you know, changes the polarization to splits to the left side or to the right side. And what it does is essentially these little holes, and you know, these polymers are designed in a way that, you know, split the polarization. So in our, you know, optimization algorithm, we have two outputs solving at the same time. So this allows you to, you know, design devices using the inverse design formulation. And then we have shown this in experiments as well, where we can split the polarization. The next thing is what we call a meta lens. So after this first successful paper, we were interested in designing a meta lens. A meta lens is this. So, you know, the glasses that we're using that have these curved shapes to be able to focus light to a, you know, a focal point. Imagine a very thin lens that is flat. You know, what you need is a specific phase distribution, which is given by these formula. So suppose you have a plane wave hitting this interface, and if this is just a thin film interface, the light will come in, some of them will be reflected back, and some of them will move forward. But if you were to focus this plane wave to a point, what you need is waves go slower at the center and go faster at these edges, right? So such that they converge to the center at the same time, so that you need to slow down the wave here, which you have a higher refractive index distribution, and then let them go faster where you have these openings. So again, this is a design that comes from the inverse design. It's hard to kind of predict this using forward design techniques, but I think the inverse design allows us to make these kind of very thin lenses. And we wanted to realize this, but also we wanted to do it in 3 dimensions. So here is the schematic, and then kind of like a cross section of the fabricated device that we fabricated using 2-photon lithography method. And here you can see that we did a kind of like scan the light to see where the waves are focused. You can also simulate this, so it's kind of like a far field effect, but also measure this in the experiments with a focal length about 8 micron or so, with a thickness about a wavelength. So you can use you can make a lens that has a thickness of the wavelength, which would be impossible to do if you were to use thin film. So I think this opens up opportunities for making very compact lenses, and I know that the Apple and Meta are using meta lenses in their late generation AR VR glasses. So there's a lot of potential in developing these kind of technologies for display applications. And then we essentially printed these lenses on the tip of the fiber, and so then use this to write down nano patterns. So this was published back in 2021 in Nano Letters. So by using a meta lens on the tip of the fiber, you can think about biomedical applications where you can focus light, so you don't need this bulky lenses to focus light. You can have a very small footprint, a compact lens that essentially allows you to integrate with fibers and access to smaller scales at ease. So with that, let me switch to the second part of my talk after a brief water break. Okay, hope you guys are enjoying so far. So the second part of my talk, I would like to discuss a recent research that has to do with sensing and detection. And this is these edge detection mechanisms using meta-surface spatial filters. So, of course, part of the photonics and image processing, there are a lot of application areas ranging from autonomous driving to biometric verification, medical imaging, and I think with the artificial intelligence tools, it's becoming more and more important to be able to quickly detect the threats and the images. You were dealing with lots of data, lots of images, and it's hard to digitally access these optical images. So what we were interested in is are there ways that method surfaces can play a role in developing the spatial filters that allow us to quickly detect the photos or edges of critical threats. So, and this is an optical image processing method. If you compare the digital and the optical processing, anything with the optics has a lot of benefits, right? So I don't have to convince you that you can make things ultra fast because of the speed of light, that you don't need the high power consumption that electronic circuits do. You could do this with low power consumption, and allows you to do parallel processing through wavelength, multiplexing and demultiplexing. However, as I mentioned, there is a curse with optics and photonics that if you deal with nanoscale materials and devices, there is this size mismatch, and then often we had to deal with bulky, larger scale, where electronics has the benefit of you can squeeze electrons to a small, tiny, because the electron's size is not there's no mismatch with the electrons. So if you are photonics undergrad and interested in next generation photonic technology, so make sure you understand this problem as a size mismatch between photons and nanoscale matter, and try to find a solution how easily and better I can interface these two different dimensions. There, I think would be a lot of because in my belief, there was this electronics revolution that happened, and I think we're on the verge of a photonics revolution. So, but there are problems, as I mentioned. So if you are aware and then looking for solutions to find how we can better address these challenges, that would be a great benefit to the society. So we're interested in developing, optical solutions, and then so there are different approaches in the literature, and I think relying on different resonant schemes. But the main challenges are that there is no polarization control, and typically as they rely on resonances, there is a narrow operation bandwidth, and they had to work with coherent light sources. So now, if you think about this application that we have in mind, so it's called the edge detection. So how fast you can process an image. So with the conventional processes, you need to image the entire image. So, but if you would like to do like a quick scan, quick detection, what you could do is just look at the edges. So if you have an idea about the edges, that would give you an idea about like what that threat could be, right? So that's called the edge detection, is used widely in trying to minimize the time to be able to detect these threats. So, and the edge detection is essentially is a second order derivative. So you have a transfer function, right? So if you have an image, and at the edges there is a discontinuity. So if you take the second derivative of the function, so you have, of course, with the Fourier transform, you can come up with a phase and a intensity response. So here we have a constant phase. So the red line shows the phase on the right axis here. So in a surface, we need to make sure that the entire surface, the phase is constant. And then there is a quadratic function for the transmission. So if we can satisfy the transmission as a function of position with these quadratic dependence and make sure that the phase stays the constant, we might be able to design a meta surface. And we, again, map out. So again, this is the part where we use electromagnetic simulations a lot. we're basically mapping out the width and how the transmission and the phase changes. So with given width of these parameter, you have points in which you have specific transmission and phase distributions. So I can pick a specific point from here and here. What I need to do is to be able to satisfy this at the same time. The phase and transmission profile needs to match the design guidelines that I have. So then we picked a specific design wavelength of red wavelength, 660 nanometer, and as a function of position, we're literally like point by point placing the right size resonators. And here is the experiments. Sorry, these are all simulations, the transmission and the for the required and the simulation. And you can see that we have somewhat, flat with, of course, some differences, at red, green, and blue wavelengths. And here we tile them up in a kind of a schematic way. And here's the fabrication. So then we measured the transmission profile. So 0 is kind of like at the center here. So we make sure that the center is like, a metal. And then as we go towards the edges, you have less metal and more air. And you can think this as an amplitude mask in a way. But an amplitude mask designed in a way to have a specific transmission and the phase profile. And here is the experiment. So what we do is we have a setup where we use an amplitude mask and then a 4F system. You have lenses here, and we're focusing light to a CCD camera. And we have this, what we call meta surface spatial filter. So we can put it in and out to see how the image differs. So here on the left-hand side, it's the same experiment actually for Northwestern logo and our famous Wildcat, the mascot of our school. On the left, in both images, is the data without this meta surface. So you have an amplitude mask, and the light goes through these openings, and you see the entire image. And this is for green laser, and this is for the red laser. And on the right of both images, what we have is the meta surface filter. So it essentially allows you to do what we call an optical computing in a way. So this is an ultra fast computing, taking the second derivative at the speed of light. So there are now studies trying to use optical computing. And I think this is also an interesting area to think about. Of course, it requires different disciplines to come together. But what we're literally doing here is taking the second derivative at the speed of light. And this is like one application. So here on the right with the meta surface filter, you can now see the edges of these structures. And we also essentially used a partially coherent source, a xenon lamp. So the previous ones are with the laser. So here we were also able to see these edges. So it essentially lifts the dependence to the narrow resonances. And we were able to do this over a broad range of wavelengths. So I'm not following time closely. Let me know if I'm getting closer. So because we started late, you can raise your hand and say that we have 5 minutes or so. I have 2 minutes. Okay. So then I will maybe quickly wrap my talk with the latest application that we have in mind. Maybe skip the introduction. But what we're really interested in is interfacing quantum emitters with resonators. And we developed a technology that allows us to disperse quantum dots, which are quantum emitters, into these resonant meta structures. And I think I don't have time to discuss this in 2 minutes, but what we're trying to do is build a very high quality factor resonator that allows us to interact the light matter interactions very strongly. And this is based on what we call the bound state in the continuum. So I think, long story in short, what we need is a resonance that has a very narrow peak. And one way to do it is what we call these BIC resonators. And we designed this structures with a given periodic boundary conditions, specific geometry. Again, in the interest of time, I'm moving quickly, and fabricated these structures that has the narrow resonances in simulations and experiments that are matching at the wavelength. And so the resonance structures allow us, because the quantum emitters have very small scattering, absorption, and emission cross-section. But if you have these resonances, you can enhance the light-matter interactions, modify its electromagnetic environment. And there is a famous Purcell factor, which relies on the quality factor as how narrow this resonator is, as well as the mode volume and how small of a mode volume that you can focus light. So we have shown this, calculated the Purcell factor. At the resonance wavelength, you see a significant enhancement of the Purcell factor. We fabricated these structures, and we were able to narrow down. Here we have a cadmium selenide quantum dot, which is embedded in these polymers. And we were able to narrow down the emission line width. Again, this is a sign of a strong coupling. And later on, using another method, the guided mode resonances. Let me skip this. This is another narrow band resonator. We were able to not only enhance the emission, but also make the lifetime shorter. So this is a paper in preparation. But again, I think this requires a lengthy discussion. So I don't have too much time to go over that discussion. So I think with that, I would like to conclude my talk. I hope I was able to convince you that there's a lot to do with metasurfaces. I wanted to focus on applications that I can highlight and that have of importance to this community here. I have other works that I don't have time to talk about. For example, we work with DNA and assemble them and make nanostructures. You can make negative index of refraction. And then we just made a nonlinear optical metacrystal. And we're also using machine learning to make the nanophotonic design. So if you're interested, you can check these papers. But with that, I would like to thank my group members, as well as my collaborators and funding agency. And of course, to you all for attending my talk, and also online community. Hope you enjoyed my talk. Thank you so much. I don't know, how do you want to ask questions? So typically, there's a question over there.
So thanks a lot for this great talk. I want to ask a question about the first subject that you were talking about the inverse design of the lens. You showed that with this inverse design, you get this kind of random constructs, right? So it looks very chaotic, you could say, but you get a beautiful result out of it. How does this compare to the result that we would know from the Fresnel lens? If you would have a perfect blazed surface, let's say, how does this compare with this result?
Yeah, that's a great question. So yeah, actually in that paper, we also had a comparison with the Fresnel lens. So we are doing better than the Fresnel lens, as far as I can tell. So we did a systematic analysis, and so I think the problem, I wouldn't say the problem, but the inverse design is an optimization, right? So there's a lot of, local minimum and maximum that might give you a somewhat, result that's not the global maximum, not the fully optimized structure. So I'm not like one of the optimization people, but especially within the context of this research, this particular study, we compared it with the Fresnel lens, and I guess the our results were better in terms of the conversion efficiency. So, but we're not claiming that this is the best inverse design structure, because I can get a slightly different design. If my student were to run this the next day, she will get a different design probably. So that's kind of like the thing that we. But yeah, that's a very valid question. Thanks. Thanks so much for the answer. Any other questions?
I am glad you are enjoying IYTE and Urla. It was a great talk. I am not I mean, I synthesize 1, 2, 3-dimensional nano structures. So I am not into photonics, so it could be a very naive question, so just forgive me if it is. Now, photons interact with electric charges. Let's say I have particles and particles have electric charges on them, because the first part of your talk said something about that. As I said, this could be a very naive question. Now, when we produce those particles, for example, we could create films around them. But in those films, depending on the ionic strength, we could arrange the gradient and the charging quantity. And also we could reverse it by, let's say, alternating fields. Would that affect, just curious, would that affect the behavior of,
So can you repeat the last part? So what are you changing?
let's say if I have a film of a liquid around those particles or surfaces. Liquid or anything. Because I assumed you are talking about in vacuum or in air or, okay, if I had a thin film of liquid, then I would have ions in that liquid, and then I could change the gradient of the potential field, and also I could reverse it if I applied an alternating field, for example. Would that affect the photonic behavior or the behavior of photons?
Yeah, I think that's a very interesting question. So I think as long as the charges interact with the photons, there would be a change. So right now we're interested in conductive polymers, for example, that rely on the ability to change the conductivity within the film. So if you're liquid, for example, this particular study, we have a DNA which is conserved in liquid.
Yeah.
Although we don't have the charges attracting here, but it's possible that if you design a material that allows you to, because there's some materials with the photons, you change the charge, and once you change the charge distribution, that changes the optical response.
That's
and
what
the ability to, once we have the electric field strong at a very nanoscale level, then even a small change in the charge would dictate itself as a big optical response. So with these techniques, we are seeing a lot of enhancement in sensitivity and detectivity of like, let's say, biosensors and photodetectors and so on and so forth. So I think as long as there is a mechanism that leads to a small change that might be amplified with the techniques that we're developing, because we were able to enhance the light matter interactions very strongly at the nanoscale.
Okay, just to repeat it, let's say I have a film and I can change the charging characteristics or potential in that film, that you are saying that would affect the behavior.
Yes.
Thank you.
We can discuss later.
Okay.
Well, I guess that's it. Thank you all.
Thank you very much, Professor Koray Aydın, for your insightful and inspiring words. We are truly grateful for your presence here today. Now, I would like to invite Professor Dr. Yann Amouroux to the stage to present a small gift appreciation to Professor Koray Aydın.
We will have a short break, like 10 minutes, but I will invite all of us to the front of our building
Nasıldı onu? Değil mi?
Cao. Professor Cao received his both bachelor and master's degrees from Harbin Institute of Technology, and he earned his PhD degree from Tsinghua University in 2005. Then he became an assistant professor at the Department of Precision Instruments, also in Tsinghua University. He is now tenured professor and director of the Institute of Optoelectronic Engineering at Liangcai University. He was a visiting scholar at the UC Santa Cruz and MIT in 2009 and 2014, respectively. His research interests are holographic imaging and holographic display. He is also a fellow of the Optica and the SPIE. Today, he is going to talk about intelligent photonics, a disruptive technology to shape the present and redefine the future. Professor Cao, the floor is yours.
Thank you very much, dear friends. All right. Now I'm attending a conference, and it's my great pleasure to online on intelligent photonics and for the Department of Precision Instruments in my university. So the title of the talk is the intelligent photonics, a disruptive technology to shape the present and redefine the future. As we know, for the human being, we have the mechanics of electronics. So this is just about the tangent fields. And in the mechanical age, we can using mechanical tools or stuff. So we have the car, we have the different communication systems, and then we have the electromagnetic age. Now we are in the electronic age. So that's information technology era. So in our university, for engineering, we have the Department of Mechanics and also the Department of Electronics. So here, this is the concept of advancing for human beings. And for electronics, we have more and more because the number of the transistors and resistors on the chip doubled in 24 months. So this is a very important for electronics. So in the computer, you have your CPU, and then you can use your CPU to handle computing tasks for the operating system and applications. And now we need another CPU, that's a GPU. We need a GPU to process data in parallel for machine learning, video analysis, and other tasks. And for the CPU, we know very famous companies, for example, Intel and AMD. But now for GPU, we also have NVIDIA and different companies. So by using CPU and GPU, we can process the information. With the help of GPU, in 2022, we have the ChatGPT. So ChatGPT follows an instruction in a prompt and provides a field response. So galaxies are picking the wood by storm. And in 2024, the solar has created galactic and imaginary videos for test instructions. So currently, we can watch the videos from the website with a lot of generation videos. So AI becomes the global spotlight, and the technology change increase their investment in battery applications to dominate the AI market. For example, in the United States, we have Google, Microsoft, and Apple, and we have Baidu, Alibaba, and Tencent. So what these companies are developing AI platform for the near future. And in September, there is a paper published in Nature that's a deep outline. You can see this pig, and for this green line, this is a human participant. So when you doing the problem solving, and then you can using a DeepSeek. DeepSeek is a kind of software in China this year. And the DeepSeek, you can see it can under about 2,000%, and computer can see, can design, and can solve the problem about the participant. So that's very dangerous because the computer can solve a lot of problems in the large language models and through reinforcement learning. So for us, if I just using the computer just to think or using the computer, the human being will be used. Why? Because the computer is above the human performance. So last year, we have the global committee recognized the transformative power of AI for physics prize and also the chemistry prize. Because we have neural networks and for physics, and also neural networks for solving the problems. Because now when we solve a problem of physics or chemistry, there are a lot of parameters. However, we use AI to train, so the problem can be in another direction. We cannot use a lot of equations to solve the problem. We can just using the neural network, using a model to solve the problem. So that's the power of AI. And as we know, the modules are most from photonics, and we also using machine intelligence to matching up photonics. And AI can empower photonics research, making a big impact in imaging, display, sensing, and communication. And you can see here, this is a video from the Princeton University, and we can use a very, very tiny studies, and then you can do the imaging. Compared with the compound optics, the effect is almost the same. So this is called the neural optics. And also for the holographic optics, you can see this is a conventional wave propagation model, and this is a learning physical waveguide model. You can see the quality is really improved. Also, we can use this for AI sensing and also AI communication. So the traditional optical system has been replaced or partially replaced by the AI. And if we can using the website and using AI to search at the keywords, and you can say this is the term. And in the past 10 years, so there is not too much research on AI economics. But the past 10 years, it increased greatly. So you can see AI economics is a new topic in our field. This is because the small change. You can say here, from 1980s to 2012, and the model is a double 24 months. However, after the for the NSNet and the ResNet, and also the convolution network, and it's double 3.4 months. Even currently, it's double every 2 months. That's because the explosive growth in computation. So a lot of the forecasting for AI technology can be changed because of AI. And another issue is that we must use the microchip. However, the microchip has to be double and 3 nanometers. For 3 nanometers, it's almost the atom level. So that's the physics image. And also for the memory processor, that is also a physical image there. So, mostly using the AI to do the processing, we have some techniques. And you can say here is another issue. That's energy consumption. And you can say the power percentage for IT technology. As you know, when you go back home, you can use the heater, using the microwave, or using different electronic devices. But now, the router, the cell phone, and also your computer using a lot of energy. So it's easy to understand that, for example, 2040 or 2050, the consumption of energy should be about 40%. As you know, there is a chess competition between the computer and human. There's AlphaGo and a famous player, Yashar A. They can play chess at the same level. But as you can see, for AlphaGo, we have 176 CPUs and also 1,202 CPUs. So the power is 150 kilowatts. But for human, it's a very small brain and using a very low energy consumption. So when we're using a GPU to process the AI models, we also facing the energy issues. There are some research about for AI. For example, from the MIT Technology Review, we see tuning intelligently use 1.287 kWh, roughly equivalent to the consumption of 120 US dollars per year. And also, if you are tuning a single AI model, you can emit as much carbon as credit card in your left hand. So you can say AI can solve a lot of problems, but it has the issue of energy. And in the United States, the company Meta uses nearly 50,000 H150 for AI tuning. And also in China, we have a company that also they have the over 10,000 GPUs. For this, for 10K GPU clusters, the energy is more important. So even for a network or for a university, we want to set up GPU clusters. Actually, you want to have 2 buckets. One bucket is to buy the GPUs. Another bucket is to use for the electric power phase. Yeah. So, only facing the physics need of electronics and also the energy issue. And we need to think about computing in another way, less optics and photonics. So, here you can see there is a roadmap for the optical AI. For optical AI, you can see this is the 1950, 1960, 1970, and also 1980. So 1980 we can have a whole field network. As we know, the whole field was awarded Nobel Prize last year. And so in 1990s, the research on optical computing was a hot topic. However, from 1990 to 210, the optical AI, there is a field research. Why? Because of the PC, personal computing, because of the electronic computing. So we have a lot of famous companies, Microsoft, Google, Meta, and a lot of companies, as you know, Apple. And also we have a lot of a famous series named Liangcai Cao. That's because the very successful of the electronic computers. But we are going to another era because of the Moore's law. So from 2012, in the past 10 years, we have a lot of optical and diffractive neural networks to go. So this review paper is a perspective review by Professor Gordon, Weston, Ocean, and Tigan, and Fan, and this is, a very famous world-class scientist who wrote this paper. And in my lab is Holland, and we also do optical computing. And you can say we input the pattern and also we store the database. So when using the human face to eliminate the crystal, and then we can see the correlation results. So the volume topology of the correlation achieves over 7,500 channels with the complete speed. So this speed is higher than the electronic speed. And this kind of computer is used for human facial recognition, big data identification, and remote image processing. So that's a very important application of optical computing. But this work was done, that's 15 years ago. And currently, in the past years, we have a new growth for photonics and optics. And this is a famous paper published by Life Science and Applications. And this is the light. We have amplitude, have frequency, and phase, and polarization, and space, and tempo. And then we can have the different properties. We can see the OAM, and also the check pulse application, and also the vortex speed. Yeah. So we can control the light. We can use the light in different dimensions. So integrating optical electronic chips are key to breaking bandwidth and power bottlenecks in the post-Moore era. Yeah. So we can use photonics for AI computing. Here we can have the optical hubs, and we have the input. And for A, B, and we can control the properties of the rod, and then we get the result as an AND and or AND or zero. This is a kind of logical operation. For optical vector matrix multiplier, we have the input, and then we have the AND. So here we can have a filter, and this is the output. So this is output is a vector matrix multiplier by input and the matrix. And also we have the optical convolution operation. Here this is the input, and this is the typical for X system. And for the in the spectral plane, we can have a field here. And this is a 3-layer structure. So we can realize the convolution close. So as you look for the convolution neural network, we have the different layers. And here we can have the convolutional operation. Also, now we can have the matrix here. And for the matrix, we can build the pattern and then get the differential operation. So we made a comparison between the electronics and photonics. And you say they have a different electronic computing, and also the CPU and the CPU and different setup. And the photonic computing is there because this is the computing speed and this is the energy efficiency. So theoretically, photonic chips enable 1,000 faster in computing speed and 1,000 higher in energy efficiency in electronic chips. So we can both see that now we're using the CPU and GPU. And in the future, we can use the photonic chip. So this thing is published in our unit paper in engineering, and we draw this thing. For the deep neural network, we can say deep learning can learn data representation and abstraction and performing powerful inference capability. So this is the operation of a single neuron, and this is a weighted addition, and this is vision function. And also we have the deep neural network architecture. This is the input layer, and this is the pattern layers, and this is output layer. So this is a very successful structure for AI technology. CPU can processing this kind of network very easily, and also for optics and photonics, we can do this thing. This is a theoretical network. This is a multi-layer, input layer, layer 1, layer N, and output. So here we have the NVI optic photonics network, and we show them. And also for IPM-based architecture, we can input different types, and then for this inside, we can have some message, and then the output. So this is a linear operation and a linear operation. For space-based optical network, we can use a diffraction network. This is the input line, and we have the diffractive layers. These are the diffractive optical elements, and then we get output layer. Even we can have the scanning material, we are using information to get different outputs. By changing the input and output, you can set up a hiding layer here. So this is the network. Yeah. So everything can use for computer. Every structure can use for computer. So that's a new challenge for us. So we can make a comparison among different implementations of optical nonlinear activation functions. So here you can see, and this is publicly Chinese flow, and we have all optical. We can use a phase change material, using a separable absorber and reverse absorber, and using a semiconductor optical amplifier, and also FDI to performance 0 or 1 or 10 or sigmoid different functions. So currently there are a lot of papers published in Nature and Photonics and Science and Technology. And you can say this is an idea of computing well scattering energies, enables real-time pedestrian detection. And this is a CW laser to eliminate the parity. So this is a computer, and this is the input. For the output, you can say it's a spectral pattern. So the traffic information is encoded, but you can use it for image processing. With the level of silicon photonics, and we can have a high bandwidth, optical compact, high integration, and the CMOS compatibility. So the silicon photonics holds significant applications in optical interconnect and also optical computing. So the photonic chips are effective to define the electric market in the future. So in the past 5 years, you see, there are many papers published for optical photonic transport and also optical convolution processing unit, and diffractive neural network, and the metal comp-based integrated photonic processing unit. These are all optical computers. So if we have optical computers, we are looking forward to a high speed and low energy consumption computer. So that's totally different away against the electronic computer. And also, there are some very milestones for this work, for example, there is training and interference, two fundamental processes for AI models. So in this work, there is about 160 parts for artificial general intelligence. And for the different chip, this is the optical chip. It can break away from the traditional dependence on CPU offline modeling, optical computing systems. So it's very efficient and very precise for large-scale neural networks. And here, you can see the optical computing chips enable Parkinson disease detection. And this is the EFA laser for convolution. And this is the input and the output. So you can, for the patients with Parkinson's disease, we can use it. This is a mathematical model, and we can use this model transfer to the optical system. So this is the optical computer, and we just need the information to calculate and to do the detection and therapy. This is a network by a Chinese scientist, Professor Wu, and this is a miniaturized diffractive neural network, enabling all optical image transportation through multimodal fiber. You can say this is the input rate, and this is the fiber. As you know, at the end of the fiber is a speckle. So you don't know what's happening. However, you can use this three-layer structure to calculate, because you know the transmission metrics, and also we can design, and the speckle passes the three layers, and it's optical reconstruction. So that's very important, and we can use the computer to do everything. You can reconstruct the output. So this is all optical image transportation through multiple fiber using a miniaturized diffractive network on the pixel chassis. Yeah. And in this year, in April 9th, there are two papers published. And one is the Chinese coverage is a land intelligence, the other is a land manual. So they published the paper in the same day because they discovered two OPU, optical processing units. So this is a for land intelligence, it's an integrated large-scale photonic accelerator piece. And the land manual is a universal accelerator. So this is a photonics circles. Yeah. And also, AI photonics research published by Microsoft Research, Cambridge, and also the UCLA Research. And for Microsoft, the analog optical computer can realize 100% more efficient than medium GPUs. And for UCLA, for Professor Ozan, you can see the optical generative models for efficient and scalable inference tasks. So what a sustainable generative AI. So this is published in September and was worked. So in this year, the optical AI has published a lot of information papers in this topic. But 7 years ago, there is no paper about this work. So you can say this topic is growing very, very fast. And we can also use the different crystal photonics for vector copy. So you just come this month to realize the high resolution spectrum. So for the photonic computing technology games, even the Intel and different companies, they are doing the optical computing and also the quantum computing. So to solve the problem of electronic computing, optical computing, and quantum computing become very important. So you can say this is a photonic supercomputer. That's the paper published in Academic Spectrum. Said the future of the energy needs of the neural networks. In this work, use there is example, you can multiply with light. It's a light speed. This because the photon and the electron are totally different particles. So I would like to propose the intelligent photonics, this topic. As you know, we have the information objects. For information, now it's not only information, it's intelligent. For objects, not objects, photonics. So we call it intelligent photonics. This is a very important keyword. However, for our universities and also for our courses, it's difficult to cover what cutting-edge topics in our courses or in our classroom. So for our students, for our young generation, we need to name at least 4 topics in your mind. The first is the meta, the second is AI, and the third is the hollow, and the third is quantum. So this is very close system. This is the microelectronics, this is the computer science, this is the optics, and this is quantum physics. Totally different ways. So if you want to learn more about the you can start from this 4 topics. So we will get a new system. It's a mix of these 4 topics. Of course, we have other topics, but I remember these 4 topics is are very important. So we have intelligent photonics here, and this is the digital world, and this is the physical world. So this is the photonics, and this is intelligent. This is the intelligent photonics. And we have the AI, meta, hollow, and quantum. So I would like to introduce these 4 topics respectively. First is AI for photonics. So AI empowers optical display, design, and materials. For example, this is a system developed by our group, and this is the lens imaging. With a very compact lens, we can get an image. However, if we're using a lens, just the FDA mask here, we can get the center image. That we can use AI to extract the image from this center image. Without the AI, and also for automatic display and the center design. And photonics for AI, we use this kind of photonics to process in the unit. We can simulate the by using the optical circles. So AI is the future engine of photonics, and photonics is the new platform of AI. So we have the AI for photonics and also photonics for AI. Yeah, this is forward modeling, and this is the inverse design. So I think most of the students can train this kind of systems. So in this paper, we listed the typical milestones in this work, and this is AI for computational imaging, and AI for inverse optical design. And for computational optics for AI, we have the coherent nanophotonic circles, or optical spiking neural network, and the diffractive deep neural network, and the nanophotonic neural medium, a lot of systems. So AI for photonics and photonics for AI is easy to understand. Let's see another word, meta. Meta photonics. So compared with the conventional reflective, diffractive optical components, meta surface possessing dominant advantages. So just now we have a very nice talk by the speaker, and we have just 1 hour talk about the meta surface, because the meta surface is very powerful. It's ultra compact for factor, low absorption loss, and ease of fabrication and integration, and flexible control of light fields. So we can control the polarization, can control the wavelength, and also the amplitude and phase of the target But you can see here, this is a timeline from 1940s to up to date. This is the metamaterial, and this is the artificial intelligence. So we have the AI, machine learning, deep learning, and deep neural network. So this is a very important year, 2011 and 2012. And also the story happens to the metamaterial. We have the metamaterial, have the meta surface, and the information meta surface, and the intelligent meta surface. So they are crossed here. So here, AI and meta are fused. So we can use in the deep learning to do the inverse design of meta surface. And the deep learning can use in the intelligent control of meta surface. Yeah. And also meta can use for AI. We can use in the different meta surface to reconstruct the optical neural network. Yeah. This is very important. So by using meta surface, we can modulate the net field, because we can use the meta surface here or freeform lens here. And then we're using a measurement. We're using a sensor or CMOS sensor here. But the information is totally compressed. You can use a very limited number and a very limited pitch size of the sensor. So this is a physical layer. Fortunately, we can use a digital layer. We can use the network to solve the problem. So this system is very important. Every system, you need to know how to modulate and how to detect and how to reconstruct. So this is a whole from the physical system to digital system. And for currently, we have different optical processing, different computing systems. But the difference is that what percentage for physics and what percentage for digital. If it's all optical, so there's no digital layer here. Yeah. So here we say we have the AI meta surface, AI for meta, and the meta for AI. This is the different systems. Another word is a holo. As you know, holography was awarded the Nobel Prize in 1971. Holo means whole, all of the information. But previously, we could not get all the information. We only get the amplitude and phase. But currently, we can get a lot of information, high dimension information of the optical and photons. So for holography, we can capture, store, and transmit optical data. And we can use the AI to do holography. For example, this is a 3D object, but we only have the 2D imaging sensor. And this is a hologram. And then we can use the deep neural network to reconstruct the object. Yeah. And also, we can use the AI for real-time denoising and AI for super resolution. So for holography, we can using AI to training the computer-generated holography. This is a very typical problem in optics. Previously, we must using the GS algorithm or traditional algorithm to do that. But now we can use AI to do. So it's very fast. So there is a roadmap of computer-generated holography. And you can say a lot of groups working on this topic. And also in the past years, we have the typical holographic AI. So this is developed by Stanford University and MIT. And in MIT group, they are developing the very, very high resolution reconstruction. And also in Stanford University, they can using the AI to address the spectral noise in holography. So when we got the using AI to generate the hologram, and also we can use the AI to generate the meta surface, and then we get the object. Yeah. So this is a combination AI, holo, and meta. Yeah, together. So hollow can also be used for AI because this is a diffraction from the input plane, diffractive layers to output plane. This is also the holographic inspired neural network. So we can design this kind of works. So there are a lot of optical neural network and computational imaging. So that's a ONN, optical neural network, enable high speed, high dimension, and high precision imaging. So this is ONN based on DOE, based on LCOS, and also based on the meta surface. Yeah. So here we have the AI for quantum and for holography and also holography for AI. Another topic is the quantum. So as you know, the quantum computer breaks the speed record, and the Jiuzhang 3 quantum computer prototype solve the complex problem in microseconds. And the Canada's company computing architecture is able to scaling to 1 million qubits through the optical networking. And also Google has developed a new quantum chip. We know it's pretty fast. Yeah. And in China, we also have the quantum photonics, a number of people working on this topic. And this is a global quantum computing market. Yeah. And this is a Liangcai is a famous Chinese company. They are driving computational power transformation with photonic chips and quantum computing. So there is a paper, so artificial intelligence for science in quantum, atomistic, and continuum systems. So you can say AI and quantum are deeply fused. So here we have the AI for quantum measurement and experiments, and also AI for quantum device design. And we also have the quantum optical neural network. Yeah. So this is the AI for quantum photonics, and this is the quantum photonics for AI. So I gave a brief introduction, AI, meta, hollow, and quantum. So the applications of intelligent photonics is metaverse, biomedicine, automatic driving, astronomy observation. So with in this setup, we have the AI technology. Yeah, you see. So this is the applications of the artificial intelligence and the intelligent photonics. And we have the holographic display, VR, AR, image recovery, and microscope and the telescope. Yeah. So this is a paper. The same title is Intelligent Photonics, a disruptive technology to shape the present and redefine the future. And this is published in engineering. You can get access in the SWell website. And this is a QR code of the paper. And you can say, here we gave the AI for photonics and the photonics for AI in this paper. Yeah, you're welcome to download this paper. Yeah. And to finalize my talk, and I would like to introduce some journals I'm serving as an editor. The first one is Advanced Photonics. This is published by the Chinese Laser Prize, and so you can read cutting-edge papers from leaders in optics and photonics. So you're welcome to submit your best work to Advanced Photonics. And also, there is a sister journal, is the Advanced Photonics Nexus. So I'm processing the papers for optical imaging. And another paper, another journal is Photonics. So Photonics aims to present brave endeavors in promoting crossing discipline research. So now it's ranking 6 over 125 in the optics category. So you are welcome to some paper to this journal, and this is collaborated with the Spring Open. Yeah. And there is another journal is Advanced Imaging, and as you know, the editor is Professor Jigan and Sao and Xu. Yeah. So this is a newly open access paper journal. And for intelligent optics, we have the IOptics here. So it's an international open access English journal focusing on integration of artificial intelligence and optics. So you're welcome to submit your related papers manuscript to this journal. And another journal is Geophysics Photonics. So since 2018, so this journal has launched, and over 450 papers published. And I'm sure there are some editors from your country, and so now the journal has an impact of 8.4. So you are welcome to submit your paper to iopscience.org and Geophysics Photonics. So that's all my talk, and this is our lab, HoloLab, it's a holographic lab, and this is a QR code. You can visit our website, and thanks to all my group members. And in our group, we have half of them are doing holographic imaging, and also half of them are doing holographic display. So we are looking forward to your feedback and your questions. Thank you very much.
Okay, thank you very much, Professor Cao, for this very inspiring presentation. Now it's time for the questions. Yes, there's a question from the audience.
Thank you for this great talk. I was wondering, you talked a lot about neural networks, and in these, in the types that you said, based on all kind of different methods, most of them have rectified linear units. So are there any optical neural networks which can actually have this real sigmoid functions or other nonlinear functionality, which would be improving on, let's say, the electronic counterpart?
Yes, thank you for your question. I'm trying to understand your question, and now for the optical neural network, the first paper, the important paper was published in 2017 and 2018. So it's just 7 or 8 years. So after that, there are a lot of groups joining this topic. And so now there are different optical systems we can use in the DOE or metaspace. But now a lot of works are working well in terahertz band, because terahertz wavelength is longer, so it's more easy to simulate. And currently, there are also companies trying to integrate them by using the macro optics and nano optics setup. So now there are two problems. One is the efficiency, because when light transmits to one phase, so one layer, there is a loss in efficiency. And the second is that the accuracy, because currently for the input, when we have some change, but the output, maybe the change is not accurately. So that's another issue, because we can have a very low resolution detectors. The detector now can be very good for imaging or sensing, but for computing, we need new systems. So as to your question, we need to develop new devices, new materials, and new channels for the optical system for real applications. Thank you.
Okay, any other question? Okay. Professor Cao, I have a small question, maybe the continuation of the previous one. We have understood that optical neural networks and photonic computing can be described as the faster and more energy efficient alternatives to electronic processors. What is the main technical bottleneck limiting the large-scale implementation of those technologies currently, for the moment?
Yeah, thank you very much for the question. So the bottleneck now, I think, is material, because as you know, when we develop the fiber transmission and also the imaging sensor, because these two technology has been awarded the Nobel Prize. The advances, the bottleneck was the principle is easy, but if you want to use it for real applications, I think we need to develop new materials for new elements for optical computer. So I think this is a chance for our photonics guys, because currently we have the AI empowered of photonics. So during this area, there is a lot of AI companies and also the government support photonics to go away, to go far in this field. But we need to develop real applications. So currently there are a lot of paper, but there's no application. That's a problem. So we want to develop a new material or new devices for the computer, and then we have the new chance for optical AI. Yeah. Thank you very much. Have a good day. Thank you.
Bye. Have a nice day. I am really glad to invite Professor Ümit Demirbaş. Professor Demirbaş received his both BSc degrees in both physics and electrical engineering from electrical engineering, and his master's degree in material science from Koç University. He earned his PhD in electrical engineering from Massachusetts Institute of Technology in 2010. He worked as a postdoctoral researcher at the University of Constance and founded the Laser Technologies Laboratory at Antalya Bilim University in 2012, where he continues to lead research activities. He is currently a professor at Antalya Bilim University and a laser scientist at the Paul Scherrer Institute. Dr. Demirbaş has published over 80 papers in laser physics and ultrafast optics, and he has received several awards, including the TÜBA Young Scientist Award, European Union Marie Curie Career Integration Grant, and Alexander von Humboldt Fellowship. Also IEEE Photonics Society Graduate Student Fellowship. Okay, please, Professor Ümit Demirbaş.
Okay, thanks, Hocam, for the nice introduction, and thanks for the students for the invitation to be here. Actually, I was here, I realized, more than 10 years ago, in 2015. I think this was when the photonics department was starting here, roughly. Currently, I am working in Antalya University, and I started to work at PSI the last 2 years. PSI is a research institute in Switzerland. It's in the border of Germany, and this river is Rhine River, the Rhein-Neckar. Okay. Today, I was thinking what to present over the weekend. The controller is not working somehow. Maybe I do it by hand. I was trying to decide what to present for today, and since to the student organization, I said, let me make it less technical Okay, so I will start with my path in optics. I'm doing research in the optics and photonics field for the last 25 years. So I want to mention what it has been for me as an example, who is a guy from Turkey, and the last 25 years, what I have been doing in several different positions. Then I will start the technical part on how we generate terrors and why it is useful for solid state physics. Okay, this is me 25 years ago. I was an undergrad student at Koç University, and I started doing research as a freshman with Professor Alpan Senderoğlu. At that time, it was basically my start to research, where I learned how to prepare laser crystals. This is Professor Mehmet Somer helping me. How to polish them, how to get their spectroscopic properties like lifetime, emission, absorption, then how to build them. So this is a laser working, actually it's a chrome zinc cyanide laser. We don't see the pump, and we don't see the lasing, but it works around 2.5 micron. So this was basically my start to research in optics and photonics. I did my master's with him also, so I still remember it as a very nice 6 years where I really learned how to do research. Then I went to MIT for my PhD. There, I learned how to create short pulses with lasers. So usually lasers work in continuous wave mode where you have a constant output, but we can mode lock these lasers to generate like 10 femtosecond, 5 femtosecond pulses. This is the first thing I learned there to build these lasers. And Professor Fujimoto, my PhD advisor, was a biomedical guy. He's the founder of optical coherence tomography, actually. He's now about 68, so I hope that he will get Nobel Prize in medicine in one day. Fingers crossed for him. From him, since he was a biomedical guy, I learned some biomedical imaging also. I didn't do optical coherence tomography, but I did multiphoton imaging with a collaboration with Harvard Medical School. Basically, you shine femtosecond light into biological tissue, and you use nonlinear effects like 2-photon absorption, 3-photon absorption to get high-resolution images. One other application I learned there was lasers. We produce pulses. Let's say your laser produces 100 femtosecond pulse. But if you look at the timing, this timing can be really very good that you are close to the quantum limit. So if you build your laser very smartly and you eliminate all the mechanical noise, thermal noise, this is actually as precise as sub 1 femtosecond, even attosecond. So that's one other thing I learned. Basically, I spent 2 years on learning how to build femtosecond lasers and 1 year on each application. This was the things that I learned in my second career path. So each position brings you something new. And for my postdoc, I came to Germany and I worked with Professor Alfred Leitenshofer. For those of you who might be interested, I used Humboldt Research Fellowship. This is a very generous research fellowship for postdocs or experienced researchers also. I should mention that this is much easier to get than an ERC grant. So ERC is now very tough. This still, I believe, has an acceptance ratio of 20%. So if you are planning a postdoc or a few years on sabbatical in Germany, I would recommend. It's quite nice program where you can also learn German. So it has family allowances, so you can travel the country. There is a small program. So if you end up, I suggest you to consider it if you are considering research in Europe. There I learned fiber lasers from Alfred's group for 1 or 2 years. It was a short period, so I'm not sure if I learned it because in research, you usually need, I think, 5 years. Then you need to publish at least 10 papers on a topic, then you can claim, I know this. So in our experimental work, so this was a very fast program for me because I had a nice offer from Antalya, which is very close to my hometown, Sparta. So I'm still there after 15 years. And of course, once you become a professor, you learn how to service, how to teach, how to get funding. So proposal writing, I have been writing several proposals each year so that we can have a lab. And we have established a laser lab in Antalya. So it was funded by European Union, Turkish Science Foundation, and my university. The lab is still active. We are still writing we are trying to write one proposal each year. So we have some research ongoing. Besides me, there is Yusuf Hoca now, Yusuf Öztürk, and Serdar Hoca as an assistant professors. So we are trying to have some critical population to do research. If you are just yourself and trying to do that, it's very difficult in Turkey. There is nobody to talk to and so on. So we are a group of 3 professors, and we are trying to keep this lab active. If I can complain, I can complain that this TÜBİTAK support is now very little, like 50,000 per 3 years. So we try to write one project each so we can do something meaningful. Okay, then I was at Germany for 6-7 years at DAISY with Professor Franz Kartner. He knew me from MIT and he was offering some positions. And at some time I said, okay, let me take a 1-year sabbatical. This ended up being 7 years with him. There, okay, I was knowing lasers and some applications, but the lasers I built was nanojoule energy, watt power. And there I need to learn joule level energy, so 6 orders of magnitude higher energy, kilowatt average powers in femtosecond systems. So this was a quite tricky. I remember my 2-3 years, the first 2-3 years, very painful because, okay, you know lasers, but it's something totally different and you need to learn different tricks. But there I learned about cryogenic lasers, thin disk lasers, high energy, high power lasers, and I started to do a little bit of terahertz generation with him. So for students, I should mention that there are summer internship programs at DAISY and at other places. You can just search. In DAISY, I was also involved. The program took about 100 students all over the world, and it's paid. The accommodation is free. There is reimbursement of travel costs, so it's quite attractive. They took, I think, 1 or 2 students from Turkey each year. What you do is you take courses in the mornings, and in the afternoon you do research with a professor you select. Okay, so if you are considering internships as a students, I think this is open to undergrad, but also early master students. So you can have it, keep this in your mind. There, as I mentioned, I won't go into the details, but I learned how to build high power lasers. This is my scientific baby, I can say. I was the scientific designer of this thing. Since I know about laser crystals, spectroscopy, and so on, we start with learning everything that we can learn from this ytterbium yield crystal. Maybe you know ytterbium YAG is now quite used in thin disk lasers and so on. The advantage of ytterbium yield is you can cool it to 80 Kelvin and it still has a broad bandwidth. So when you cool ytterbium YAG, on the other hand, the emission bandwidth gets very narrow and the pulse width you can get is 5 picosecond. With ytterbium yield, one can still get sub 1 picosecond. Here we have 1 picosecond, but we are improving the oscillator to get it sub 5 femtosecond. So you can build a kilowatt level amplifier with 500 femtosecond pulses. This took actually more attention over the last years, because if you remember, in December 2022, there was this Lawrence Liverpool National Laboratory. After 60 years of effort, they showed that in fusion, they get more positive energy than what they put into the system. So this initiated some research efforts again after the 60 years in Germany. I just was reading this memorandum. Germany plans to spend 2 billion till 2029 in fusion research. There is already 4 startups in Germany. Of course, this is good news for laser research or high power laser research, because this room is all a very big laser. So if you are considering doing lasers it might become more and more attractive. And if they can really demonstrate its operation by 2045, so it will be a boost for researchers working on lasers also. Okay, this is my last group. I moved to PSI, Switzerland 2 years ago. You see, we are all 40s, 50s. I am in the Photon Science Division in the nonlinear optics laboratory under the gun laser group. I will tell you what a gun laser group is in a few minutes. When I joined PSI, they were planning a laser team, but they hired me. Then there was a budget cut in the ATH domain, and I just became myself as a free electron, no group to attend, and so on. So they put me to the gun laser group. There, I learned about free electron lasers, user operation, picket service. I will talk about this so you have an idea. But the last year or so, I started doing research also on ultrafast fan probe spectroscopy and terrestrial-driven condensed matter physics. So this is very new to me. So I'm learning, okay, I'm a laser guy. I build sources at different wavelengths, but for this position, I need to learn also now solid state physics. So a new challenge after age 45 to learn a different field, but I really also enjoy it. That is like a new PhD starting for me. So why X-ray lasers? First of all, why there is Swiss well? In very simple terms, it has a resolution advantage. X-rays has a short wavelength, and for resolution, you need short wavelength. The second advantage is, you know, from signals or systems course or similar courses you take, if you want to generate a short pulse in time, you need a broadband frequency. But there is one other knob which is more important. The pulse width you get is also related with the center frequency you have. So if you are already at a short wavelength, you see this is lambda to the square. This is very important. So with X-rays, even a narrow bandwidth can be short. Okay. So there is this two advantage to use X-rays for imaging. So you can image small things like electrons, which are small, and these small things are usually fast, and you have the fast pulse anyway. But why not use X-ray tubes that we use in computed tomography, X-ray imaging? The problem is you cannot focus this, and they are broadband. It's basically a continuum of spectra. With free electron lasers, which is happening in the last 10, 20 years, we can now build X-ray sources, which we can focus. They have high intensity. We can focus them, and they are relatively narrow in spectra. So that's the reason why we are now building everywhere X-ray lasers. And this was the team that I worked for the last 2 years. So I was in the gun laser lab. So basically what an X-ray is, free electron laser is, you have a gun. Basically you shoot an electron, you shoot a femtosecond pulse to a material, which shoots a femtosecond electron pulse. Okay, this is the gun laser. Then you accelerate this electron to close the speed of light. And after some time, you put magnets. Of course, you have a very fast electron, and you accelerate it. Accelerating charges emit photons, and you get, if you design it carefully, you can get X-ray photons here. So this thing is like 700 meters long, 750 meters long. And this was a low-cost free electron laser, actually. So it cost about 300 million. But one other thing is these beam lines that operate, it has only 2 beam lines. They cost each are more than 10,000 francs. So what the gun laser group was doing is, of course, we shoot these femtosecond pulses, so they have the operation. And these lasers should work basically 7 days, 24 hours, and even 3 months without entering to the lab. So this is really pushing the engineering. I mean, this is a commercial laser. It's not a very high profile laser in terms of, okay, this is a millijoule laser, but the challenge is to keep this laser running for very, very long time, very, very stably. How stable you want this to operate? Very, very stable, because you generate this femtosecond pulses, and the user has a sample, and then these pulses should arrive at the same time. So there are controls everywhere. This is more optics than control engineering, I can say. And if you remember, there was a volcanic eruption on the other part of the world. It is 16,000 kilometers away from PSI, but after 15 hours, we feel the pressure wave coming from this volcano in our lasers, because the volcano sends a pressure wave which changes the air pressure at Switzerland by 3 millibar, and changing air pressure means changing refractive index. Changing refractive index changes the timing of the lasers, and the motor should correct it. Okay, so this is in terms of engineering and control, this is a very difficult system which requires many people to serve, and the beam time is expensive. The user applied for this beam time 2 years ago. He wants to do his experiment, and you are the laser scientist, and they can call you, okay, we have a problem in the laser. So this was a stressful job for me, I should admit. Okay. I also, over the last years, started to research. So this is like a service. If you are a professor at the university, you teach. This service is video anyway. There is the main job also you need to do. For me, it was taking care of laser spectroscopy lab, or helping to take care of this lab. We purchased a TISA system. Sapphire systems, as you know, operate around 800 nanometer. We had 2 beam lines, one providing 10 millijoule at 1 kHz, the other one providing 25 millijoule at 100 Hertz. What you can do is you can then use nonlinear optics. Okay, this is 800 nanometer, but you can take second harmonic to go to 400. You can also use an optical parametric amplifier to go from 800 to 1.2 to 2.6. There is another DFG unit, which you can go up to 15 micron. And we have a terahertz setup here, which we can go to millimeters. So this lab was quite active during the last 2 years. We are flexible in providing what we offer, but we want to offer terahertz pump 800 probe. So what you do is, in this, you have our users as a sample. You can see it's maybe this sample with the superconductor, which I don't know. Sorry? Okay, sorry. Then this is our sample. We usually excite it. So one pulse excites it, and with another pulse, we probe it, meaning we try to understand what the pulse is doing. So one to excite, one to reveal. This is a sample excitation curve. We look at reflection, we look at transmission, we can look at phonons, Mach-nons, and so on. And the last 2 years, we had more than 10 experiments in the lab. And this is open to collaboration usually, but we are enough applications from PSI already usually. So it's a competitive application process with scientific evolution. Okay, for those of you who are new to terahertz, we are usually have a feeling of visible light, let's say 1 micron. A terahertz light has a wavelength of around 1 millimeter. So it's 1,000 times different. So when things are 10 times different, maybe you have a feeling, but this is 1,000 times different, meaning, for example, the photon energy in visible is like 1 eV. In the terahertz region, it's just milli eV. Okay, the temperature, a typical temperature for this radiation is like about 10 Kelvin. The period of the pulse, so the shortest pulse we generate in visible about 3-5 femtosecond. A short pulse in terahertz is like 5 picosecond. Okay, and also they are also open up very fast. Assume you have a 1 millimeter beam, like this laser beam, I can send it several meters and it will not get too much bigger. If you have a terahertz source with a 1 millimeter aperture, in just less than 1 millimeter, it already opens and doubles its size. Okay, so this is like we are going to the microwave domain slowly from the optical. So why we use terahertz? It is the optimum wavelength for some process. So I told you why X-rays, because they have a small wavelength and they are fast. Why terahertz? Terahertz sits in the milli-electron volt picosecond range, and this is where phonons, magnons, and spins resonate. Okay, this is good for some resonant excitation of solid-state physics. And we can generate here very strong fields, like 5 electric fields larger than 5 megavolt per centimeter, and we can have magnetic fields larger than 1 Tesla. So this allows you to do actually nonlinear phononics. So these are strong enough to do nonlinear phononics. We can really excite them, and we can really excite them very largely that you don't see the simple picture, but you see more interesting picture where you can trigger some phase transitions. You can reveal hidden phases and so on. And so far, when you look at the pump probe literature, most of them use visible light to pump and visible light to probe, because this terahertz is new. What we hope with this terahertz light is, okay, when visible light hits some system and it has 1,000 times more energy than you want, okay, you can maybe see what you want to do, but it's much more than that. You hit the sample, and it's a very complex mechanism then. But if you just resonantly drive these excitations, it has advantage that it's much simpler what you see. And if you, for example, excite a hidden phase, this phase stays there longer because there is less thermal load on the sample. Okay, this is like a cheating sheet. How do we generate better terahertz sources? I won't go into too much detail, but this is a little technical. So this is like cheating sheet to generate terahertz using intra-pulse difference frequency generation. So I have a short pulse. I want to generate a difference frequency of 2 colors. The first thing is these 2 colors should be in this pulse, meaning this should be a short pulse. Okay. And assume this terahertz frequency is this omega terahertz. To generate it effectively, first of all, I need to choose a material with a large second order nonlinear coefficient. And if you go into more, if you generate a higher frequency terahertz, it's better than a lower frequency. So it also scales with frequency square. One other thing is, it also scales with the fluence. Assume you send 1 photons and you get 1 terahertz. And now you send 10 photons, but the same area. This is the efficiency. You will get 10 times more efficiency, but you will not get 10 photons. You are sending 10 photons and it's 10 times more efficient, so you get 100 photons. So it's scales with fluence also nonlinearly. And ideally, you want to use a long crystal. This is the effective crystal length. You can have a 1 meter of crystal, but if there is absorption, if your femtosecond pulse gets too broad, or if just pass through the terahertz pulse, you won't be able to use it. So you need to design your crystal carefully. And this is the same thing as I mentioned. So you want to have these frequencies in your pulse to be able to generate their difference. So if you look at what Cosmos gave us as terahertz crystals, the first portion is organic crystals. Why we use organic crystals? Because they have the highest nonlinearity that we know. And for lithium niobate, which I will also talk about, it has also very high nonlinearity. The coherence length is, you start to generate terahertz, you have 2 pulses, your optical pulse and your terahertz pulse. If your terahertz pulse and optical pulse don't propagate together, basically they will stop talking with each other and you are not efficient. For this to be efficient, you want to have them the same refractive index. And with with organic crystals, we can do that. With lithium niobate, we can not do that because lithium niobate has a terahertz refractive index of 5, which is very strange. So we cannot really do that. But smart people earlier looked into that and they found tilted false front phase matching for broadband emission and quasi phase matching for narrowband emission. They should have a low N2, but this is also, you want a material to have very large the effective, but you want it to have very small nonlinear Kerr effect, which is not usual. As you see, usually these organic crystals have very large N2 also, which means you put your femtosecond pulse, the pulse gets Kerr focusing, it broadens, and you cannot use it anymore. For lithium niobate, we have a very low N2 also, which is an advantage. And you want to minimize the absorption of terahertz. We do it in lithium niobate by cooling the sample. One problem with these organic crystals is when you see them, okay, you will say, what is this? You will throw it away. It really looks bad. This is very hard to grow, these organic crystals. And we cannot grow them in large sizes. And we cannot grow them very thick. And when you grow them, they are really not homogeneous. But that's what they are. We still use them because they are the best. Compared to lithium niobate, where you can really grow very large samples. This is a typical setup in our lab. We have a laser source for the terahertz and the pump pulse to go together. In organic crystals, we need to use a pump wavelength of 1.3 and 1.5 in between this. So we go through an OPA. And with this, we generate, this is how the organic crystal looks. It's shining because there is parasitic second harmonic generation. Then we have this terahertz, and we have this setup to do terahertz experiments. We get about 10 microjoule from organic crystals easily. This is about 0.5% efficiency. But the field we get, this is a short pulse in terahertz, and we can get more than 5 megavolt per centimeters. We have users in PSI because people don't usually have this high energy OPA, and their fields is like 1 megavolt, 2 megavolt. So in our lab, we can go above 5 megavolt. That's we attract users from PSI and Switzerland. So we can do high energy terahertz pump, then they can see nonlinear effects. The spectra, if you look at the spectra, it covers from DC to roughly 6-8 terahertz. There are different types of organic crystals that you can choose to optimize. For example, OH1 works close to 1.5 terahertz. And we can also put filters here to choose one portion of the spectra. Okay, most of our users use these organic crystals, but we start to develop this spiky terahertz sources. Here I am plotting spectral brightness. These organic crystals usually provide a very broad frequency bandwidth. That's why they are very short in time, and we have very high electric fields. But the question is, do we really need it for all the applications? What we can do is with this periodically poled lithium niobate crystals, I can generate really very, very narrow spectra that is tunable. And one question is, I feel that, for example, this is nickel oxide. This is the magnon the user wants to excite. And if you send these organic crystals, they are really broadband. So most of the terahertz photons I sent become useless. And the second thing is, sometimes this is iron, potassium, S3. You see, I am sending this terahertz, or they are sending this terahertz, but there are many peaks, like 3-4 peaks. So what they see is the response. As a response, they see the response of all of these peaks. But this is a very difficult material. What we propose is, okay, why not just first resonate with this first phonon, the second phonon, then you excite the magnon, and you excite the last phonon, and you learn. And maybe if you want, then you can excite them all together and learn the complexity. But what our users complain is usually they measure something, but it's very hard to understand. They need to go to a theoretical guide to modulate, to simulate, and these papers usually take 1 or 2 years to publish because they are exciting many things at the same time. So we hope to propose this narrow line terahertz emissions so that our users can excite one phonon or one magnon and then they can learn it much simpler. Okay, what quasi-phase matching is, if I try to explain, so you have two frequencies and you want to take a difference frequency. You can start from Maxwell's equations, and in 2 hours you can derive these equations, which basically tells you how much they talk with each other with some nonlinear terms. What happens is, you start with omega 1 and omega 2 only. There is no terahertz. You first start to generate some terahertz. But if you are not phase matched due to this e to the j delta kz, after some time, you go to 0. So you create some positive terahertz photons. Then when you reach this coherence length, which is related to the refractive index difference of these materials, you then terahertz goes back to the pump source. So what you do in quasi-phase matching is, when you are at this point, you change the c-axis of your crystal so that you still are phase matched and you start to grow your terahertz. Okay, you continue to grow your terahertz. So with this, what happens is, we have a crystal that is part of a series of stacks, and the c-axis of the crystals we swap. Okay, we swap again, and so on. At each section, we generate a cycle, sub-cycle of terahertz. So when you send your pump, you get a long terahertz pulse. And a long terahertz pulse in time is a short or very narrow in frequency. So that's why we generate, that's how we generate narrowband terahertz. The nice thing is, okay, for this process to work, the energy conservation should work. So this is basically omega 1, omega 2, their difference should be this terahertz. And there are the momentum conservation should also work. There are many ways to conserve momentum. This is basically physics 101, where you have vectors and you try to make their size equal. Two ways that this work is, one is the forward propagating terahertz, but there is also a backward propagating terahertz that can also be phase matched. And if you do the math of physics 101, you just show that I just shine one light, but I can get one output here, one output there. They are actually at different frequencies. This one is at a higher frequency and this one is at a lower frequency. And their frequency depends on this polling period, which I can adjust, and the difference of refractive index of terahertz and optical. Okay, if I go fast now, basically we have many of these crystals in the lab. You can purchase them commercially. The small size ones are like 5,000, I believe. If you want a long one, a large one, it can become 10, 20,000. We had 4 of these in the lab, and which checked their emission. So one question that was open is, okay, it's lithium niobate, it's very well-known material, but when you ask, do we really know how these parameters like effective nonlinearity change with temperature and frequency? The answer is it's not studied. So what we first studied was, what was the optimum frequency we can generate with this material? So this is the equation, but we don't know how these things change. So this is the length, but this is the effective length, which can be suppressed by absorption. This is the effective, okay, we don't really know how it changes. And this is the pulse width. So there is an optimum. If you want to generate a small frequency, a long pulse is okay, but if you want to generate like 5 terahertz, you really want a short pulse because you want to have this frequency in your system. So having this in mind, and we cannot estimate accurately using the equations, we just made the experiment basically, where we showed that at room temperature, the optimum is about 0.5 terahertz. And at cryo, when we go to 15 Kelvin, the optimum terahertz is at 1 terahertz. And we look at how they change with temperature. For low frequencies, you just improve the terahertz by 2 if you cool down. but for high frequencies, the improvement is as high as 30%. This is because lithium niobate has a phonon around 5-6 terahertz, and this phonon's basically absorption goes down to the 1 terahertz range, and if you don't cool your crystal, it can push this to the optimum to 0.5 terahertz despite this F-square scaling. Okay, this is the time domain. So with terahertz, what is good is we can measure how the electric field looks. So in optical domain, we take an autocorrelator and so on, but you don't know how the field looks usually. With terahertz, we can do it simply with electro-optic sampling. So these are the response of different crystals. What is important here is we get very narrow spikes in frequency domain. And we can actually tune them by changing the temperature of the crystal. Okay, so here you can say we cover with lithium niobate from 0 to 2 roughly, and there is absorption. So this is not continuous, but what you can do is if you pay enough, there are crystals which has different quasi-phase matching periods. So you can just shine light at different positions of the crystal, and in your lab you can get a tunable terahertz between 0 and 2 terahertz from using lithium niobate. One other thing we observed, and this will be the last technical thing I will talk. So in quasi-phase matching, I mentioned the terahertz start to decrease at the coherence length and you reverse the crystal orientation. What you can see is if I wait long at 2 coherence length, if I reverse here, I don't gain much, but I can do it at the 3 coherence length also, and this is shown here. From this graph already, it looks like this is not a smart move usually, and we don't do it for second harmonic generation and so on. But there is a trick in terahertz. What happens is, okay, first of all, the efficiency that you do here, this is like quasi-phase matching efficiency, and this effectively decreases the nonlinearity basically. So for m equal to 1, this is, okay, 1 over m, I assume it is 1. If I do m equals to 3, actually, this is 1 over 9, so it's not a good idea. What happens with terahertz is, the frequency that it generates also scales with m. So at the end, the efficiency of this higher harmonic can be as high as the efficiency of the first harmonic, because there is an m square factor coming here and 1 over m square coming from here, and they cancel each other. And we have shown that this is actually what it is in the lab by generating harmonics up to 9. So with this, you have a like frequency comp in terahertz. You can tune them by temperature tuning, and you can change their separation by using a different crystal with a different quasi-phase matching period. So what we hope to do is, this is just like 5 lines, and we hope to generate like 20-30 lines with a different crystal. And if you tune them, we will hope to basically cover all the terahertz that we can cover from 0 to 2 terahertz. Okay, what is next for me is, as I mentioned, I am new to this topic. I am trying to learn solid state physics, phonons, magnons, and so on. So if you ask me these things 2 years ago, I didn't know much, but with each user I am learning. And we hope to offer these narrowband terahertz sources to our users to study solid state physics in the coming years. This is up to 1.52 terahertz with lithium niobate, but we have other materials that we consider. So we can go up to 4-5 terahertz, like gallium phosphide and zinc selenide. And we have a new lab also that we are trying to build, start a laser effort, but it even takes time in Switzerland, I can say. I mean, it's hopefully faster, but we are just starting where to put the tables and so on. So I don't know what is next for me, but I will try to learn as a student some solid state physics, start a new lab, and maybe hopefully build some lasers. But I hope to build these terahertz sources and perform some solid state experiments. Thanks for your attention. Thank you.
So in your last topic, you show that you have this comp, so you can have different frequencies at the same time, and you can also shift all the frequencies by the temperature. So you, in principle, can have like one frequency which you can, well, go over the whole frequency field.
That's what I will try in my next beam time. So I am hoping to buy a crystal which can provide more of these. I mean, this is like a frequency comb. They are not exactly accurately spaced, but their position is known because it comes from the refractive index data. And with temperature tuning, then I hope to cover basically all the available frequencies from basically close to 0.1 terahertz to 2.5 terahertz. And then this is like, you have a sample, you take one data. If you can change the temperature, you can be on resonance, off resonance. And if you look at your sample's property as a function of this terahertz tuning, you learn what your sample does, for example.
How do you suppress the other frequencies of your comp?
Sometimes you don't need to. When you need, we also have a collaboration with EMPA. They are developing bandpass terahertz filters, which is narrow band. But it's a challenging topic also that research needs to go there. But if you just need one frequency, I would probably just stay with these guys. They are really just one frequency and tunable within 10% of this. And if you use a crystal like this, which I couldn't buy because it's very expensive, so you don't need to temperature tune. You can just send your pump to here, you get a terahertz, and to tune the terahertz frequency, you just shift your crystal, and this will give you a different frequency. So it's possible. Probably for each user, you need to ask what you need and create a crystal for that and do the experiment, basically. Thank you.
Any other questions? Okay, thank you. I would like to
Should we?
sanırım. Announcement. There's an announcement. The following two presentations have been postponed. These two talks will be delivered tomorrow. Okay, now we have a coffee break. Then there is a workshop about outer workshop with Mr. Amouroux. Thank you.